Hello everyone. In this module, we are going to study about C13 NMR spectroscopy. Before that, we have to understand that so far we have studied in the last 9 modules about proton NMR spectroscopy, and from today, for next 2 or 3 modules, we will concentrate on C13 NMR spectroscopy. Under this, we are going to study these subheadings: comparison of proton NMR and carbon NMR, proton decoupling, of resonance decoupling, chemical shift equivalence, and chemical shift values. We will take up one by one. First, we will have an introduction about C13 NMR spectroscopy. You must be wondering now why we are not studying C12 NMR spectroscopy, rather we are going for C13 NMR spectroscopy. The reason is very, very simple. For any nucleus to become NMR active, its spin quantum number should be, that is I, should be greater than 0. So we know that in C12, 6C12, that is atomic number and mass number, 6 and 12 both are even. So when both are even, we know that I becomes 0, spin quantum number is 0. When spin quantum number becomes 0, it becomes NMR inactive. That's why we go for the next isotope of carbon, that is 6C13. Here one is odd, one is even. So we are going to get I is equal to half, like that of our proton. For even proton, 1H, we are going to have the spin quantum number of half, and hence we say that C13 is NMR active, whereas C12 is NMR inactive. Before the evolution of C13, proton NMR was the first to be discovered. Later, in recent times, C13 NMR was discovered. So it is a relatively new technique. The same principle holds good here for C13 NMR also. Here, whenever you take the carbon nucleus, it will be spinning about its own nuclear axis. When it is spinning about its own axis, it will generate its own tiny magnetic field. When I supply external magnetic field, it will orient in 2 directions, parallel and anti-parallel. When I give an external radio frequency energy, some of the nuclei will absorb the energy and it will go from ground state to the excited state, and it will not stay there itself. It will come back by process of relaxation. Whatever we have studied, the principle for proton NMR, the same thing holds good here for C13 NMR also. This C13 NMR spectroscopy, it is not as such useful for the prediction of the structure of the organic compounds alone. Whereas when we take C13 NMR and carbon, and 1H NMR, both will be complementing each other. That results in the elucidation of structure of organic compound. There are several differences between proton NMR and C13 NMR. We will see what are those differences in a short while here from now. And the main purpose of distinguishing them is because here the mode of recording as well as the appearance of the spectrum will be different. Now we will see how they will be differentiated. Comparison of PMR and CMR. Here PMR refers to proton magnetic resonance, CMR refers to carbon magnetic resonance. It is also called 1H NMR. This is also called C13 NMR. Whenever we look at the proton NMR, we see how many types of different nuclei, how many types of different protons are present in the organic molecule. That means we will see what are the different environments in which the protons or hydrogens are present in the molecule. That means it is giving an indirect information about the carbon skeleton in the organic compounds. Whereas CMR spectra, it will give the direct information about the carbon skeleton of the organic compounds. If there are 6 peaks, it tells that there are 6 different types of carbons. Whereas in proton NMR, if there are 6 peaks, we can say that there are 6 types of hydrogens, and it is giving an indirect information for us with respect to how many number of carbons or how many different types of carbons are present in the organic molecule. That is the first difference. And the second difference is the natural abundance of C13 is just 1.1%. The remaining 98.9% will be carbon 12. And also the lower magnetic moment of C13 value will be very, very less compared to the proton. So when you take 100 carbon atoms, among 100, only 1.1% will be carbon 13, whereas the rest will be carbon 12. And also carbon 13 has got very low magnetic moment than that of the proton. It is for this reason we need to increase the sensitivity while recording the C13 NMR compared to proton NMR. That means greater sensitivity is required to record C13 NMR compared to proton NMR. With respect to the resolution, here you must have remembered while studying the proton NMR, we have seen that the spectral scale, the NMR scale for proton NMR is from 0 to 20 delta. That means it is not much wider. Whereas for carbon, it is very, very highly resolved in the sense that you will have the spectral scale from 0 to 200 delta, almost 10 times greater than that of the carbon. That means here the peaks are very well resolved or very well separated compared to proton NMR spectroscopy. In proton NMR spectroscopy, we have seen that 1H and 1H will couple with each other, resulting in the splitting of the peaks. Whereas in carbon NMR, you won't see C13 coupling because only 1.1% of the carbon in a compound will be C13, and hence you will not expect C13 coupling. Rather, you will expect C13 and 1H coupling. So if there is carbon as well as there is a hydrogen, then you will see that both carbon and hydrogen will couple, but not carbon and carbon. Because what is the percentage of carbon in a compound? C13, that is, it is only 1.1%. Therefore, you will see that in a one type of carbon 13 NMR spectrum, that is proton decoupled spectrum, each magnetically non-equivalent carbon, it gives a unsplit peak. That means you are going to get only a single peak in proton decoupled spectrum of carbon. Whereas in the proton NMR spectrum, you will see that each peak will be splitted depending on the number of carbon atoms it is coupling with. That is the fourth difference between PMR and CMR. The fifth difference being, in proton NMR, we will see that these many number of hydrogens are there. Whereas in carbon, you cannot ascertain for that because the relative ratio of carbon atoms in a compound cannot be determined by the integration. So integration is lacking here. You must have remembered in proton NMR, we have seen that the step-like peaks will appear. Those steps are nothing but integration. That can be done in proton NMR, whereas in carbon 13 NMR, you won't see any kind of integration. So the integration cannot be done in CMR, unlike that of the proton NMR. The last difference between PMR and CMR is that in proton NMR, you have seen that you will get different kinds of information from the proton NMR spectrum, like coupling constant, chemical shift, and also relative number of absorbing protons. So how many different types of protons are present in the molecule? All three information can be obtained by looking at proton NMR spectrum, whereas the CMR spectrum, it will give only the chemical shift value and nothing much. So these are the major differences between PMR and CMR. Now we have to study some of the basic terms with respect to carbon 13 NMR. The first being the sensitivity. As I told you already, here the sensitivity is very, very less. That's why greater sensitivity is required for the recording purpose. The very first sentence that we will study in carbon 13 NMR is, it is very, very difficult to record CMR spectra because C12 is the most abundant and C13 is very, very less abundant. C12, it is not detected by NMR because it is NMR inactive, whereas C13, it is NMR active, but its percentage is very, very less. And also the magnetic spin is also very, very less. Coming to C13 NMR, it has got weak magnetic resonance. Because of its low abundance and low resonance frequency, CMR is very, very less sensitive than PMR. So what we have to do for this purpose is, in order to increase the sensitivity of CMR, we have to repeatedly scan the C13 NMR spectra. In proton NMR spectra, you scan it only once, you will get beautiful peaks in the NMR spectrum. Whereas if you scan only once for C13 NMR spectrum, you won't be seeing any peaks because only 1.1% of the entire molecule will be C13. For this purpose, we have to repeatedly scan, and that means even the time taken for recording C13 NMR is also very high when compared to proton NMR. Say for example, if you are taking 5 minutes for recording proton NMR, then you need nearly 15 to 20 minutes for recording C13 NMR because the sensitivity is very, very less. In order to enhance the sensitivity, you need to scan the spectrum repeatedly and stored in a computer. What about the operating frequency? We have seen that only 1.1% of the carbon in a molecule is C13. That means even the gyromagnetic ratio of carbon-13 is 1/4 as that of the proton. When the gyromagnetic ratio becomes less, the resonance frequency also becomes less. That means to say, if you are using 60 megahertz for scanning 1H NMR, you don't have to use that much resonance frequency. You divide it by 4. That means you need only around 15 megahertz for a megahertz frequency for scanning C13 NMR spectroscopy when you use a spectrometer operating at around 14,000 Gauss magnet. Because gyromagnetic ratio is also 1/4 as that of the proton, resonance frequency will also fall down to 1/4 as that of the proton. So instead of using 60 megahertz, use 1/4 of that for the recording C13 NMR plus. So 60 megahertz divided by 4 is, it comes to around 15 megahertz frequency, and that is quite enough for recording the C13 NMR spectrum. So if you are using 400 megahertz instrument for proton NMR, then here you need to use only 100 megahertz instrument. That is about the operating frequency. Coming to multiplicity, you know the multiplicity, whenever two protons couple, it will give different kinds of multiplicities. That means n+1 rules holds good for proton NMR. We will see what happens in case of C13 NMR. We know that C13 coupling is negligible or say absent in a molecule because 1.1% of the carbon in a molecule is C13. It is because of this reason we won't see C13 coupling, whereas we can see the coupling between C13 and 1H. So whenever there is whenever we say organic compound, it should have both carbon and hydrogen. So here when C13 is not coupling, there will be an advantage of C13 and 1H coupling that results in the complicated spectrum. It is because of that multiplicity of the signal depends on the protons directly attached to the carbon. Say for example, if one hydrogen is attached, then n+1 rule is 1 + 1 is 2. That means that carbon will give a doublet. Similarly, if the carbon has got 2 hydrogens, n+1, that is 2 + 1, 3, that carbon will show triplet. So it complicates the spectra. Here n+1 rules holds good as that of the proton. But you have to bear in mind here that for proton NMR spectroscopy, the protons present adjacent, that is involved in the splitting pattern. Whereas here protons directly attached to the carbon, that will result in the multiplicity or splitting pattern. That is the multiplicity difference between C13 and 1H. So because we are getting too much complicated spectra because of C13 and 1H coupling, scientists have discovered a technique that is called proton decoupling, or it is also called noise decoupling. So here, as the name itself is indicating, instead of coupling, you have to decouple. What you have to decouple? You have to decouple the proton. So here proton is not necessary for us. Proton will result as a noise. That's why we have to decouple the noise. That means we have to eliminate the noise and we have to retain only the C13 peaks. So how this can be done? It is done by double irradiating or by giving extra energy at the resonance frequency. So what we have to do in this technique is you have to run the NMR, you have to run the C13 NMR, and by double irradiating the proton NMR, you are eliminating the coupling between C13 and 1H. So because you are involving both carbon and hydrogen, it is called heteronuclear decoupling. Whereas in proton NMR, we have studied about double irradiation. There it is called homonuclear decoupling because both the nuclei are hydrogens there. Here, one is carbon, another one is hydrogen, because carbon and hydrogen are entirely different species, and that is called heteronuclear decoupling. And it is usually represented by C13 minus 1H. This is the representation of heteronuclear decoupling. So this is done by double irradiation of all the protons simultaneously while recording the C13 NMR spectrum. So it is usually what we do, we take the sample, we put it in the spectrometer and we run C13 NMR. While running the C13 NMR spectrum, you have to double irradiate only the protons, all the protons simultaneously. So what happens? Because of the double irradiation, the protons which are next to each other will not get disturbed, will not see them among themselves, that will result in the elimination of all the couplings between C13 and 1H. As a result, here all the peaks will be appearing as a singlet. So in this method, a decoupling signal that has all the 1H frequencies spread around 100 megahertz, that is a form of radio frequency noise that is used for the decoupling purpose. Here, the spectra obtained are called decoupled or noise decoupled, and this is also called proton noise decoupling. Here, noise is nothing but unwanted. If while running C13 NMR, we don't want the proton. That's why we are deleting the proton. Here, proton is treated as noise. Noise is something unwanted. That's why it is called proton noise decoupling. So whenever you use this method for recording the C13 NMR spectrum, all the peaks will appear as singlet, and that is shown here. This is ethyl acetate. Here there are 4 different types of carbons. See here, this is first carbon, second, third, and fourth. For this first carbon, 3 protons are attached. So what happens here? All 3 protons are getting decoupled. That means here protons are treated as noise. It is also called noise decoupling. So this carbon C1, it is appearing as a singlet. Here the second carbon, carbonyl, it has not got any proton. Instead of so it is giving a singlet. Here the third carbon, it has got 2 protons. Both the protons are decoupled, so it is also giving a singlet. Whereas C4, it has got 3 protons. We don't want any proton to be coupled with C13, and hence what we do here, we will decouple all the 3 protons. That results in the formation of a singlet C4. So instead of complicating the spectra, we are simplifying the spectra by means of noise decoupling or proton decoupling, and hence all the carbons will appear as a singlet, and this is called proton decoupled spectra. Coming to the next technique, that is called off resonance decoupling or selective proton decoupling. In the last technique, we have seen that all the protons are decoupled simultaneously by using double irradiation technique. But in this method, what we do is, instead of eliminating all the protons, we will do somewhat something called as off resonance decoupling. Here, mainly the sample is irradiated at a frequency close to but not coinciding with the resonance frequency of protons. Say for example, if a proton is absorbing the energy at 100 megahertz, we won't be giving 100 megahertz frequency, rather we supply 50, 60 or 70 megahertz. So what happens? Instead of coupling with the neighbors, it will couple with the attached carbon, thus eliminating the complication of the spectra. Here, the multiplets become narrow and not removed altogether, as in the case of fully decoupled spectra. In fully decoupled spectra, all the protons are eliminated simultaneously. So that results in the formation of only singlets in the NMR, C13 NMR spectrum. Whereas in this case, we see many multiplets but not singlets, and those multiplets, it can be easily compared with the particular carbon present in the molecule. Here, in off-resonance decoupling or selective proton decoupling, C13 nuclei are split by the protons directly bonded to them and not by any other protons. We have seen in the earlier case that the protons which are neighbor to each other, that will couple with each other, thereby resulting in the splitting pattern. Whereas in the off-resonance decoupling, you must clearly understand that protons which are directly bonded to the carbon only will lead to multiplicities or splitting pattern. That is what is shown here. Only one bond coupling. That means here 1H is directly attached to carbon, and this is observed. Whereas 2 bond coupling, say for example, here 1H is separated by another carbon. Here 1H is there, here C13 is there. 2 bond coupling is not seen. 3 bond coupling. So that means 1, 2, 3, 3 bonds are there. The 1H and C13 are separated by 2 other carbon atoms, and this kind of coupling is also not seen. Only protons which are directly bonded to C13, only such couplings are seen in case of off-resonance decoupling. Here, when you do so, off-resonance decoupling or selective proton decoupling, say for example, what will be the multiplicity? This carbon does not have any hydrogen. When there is no hydrogen, n+1 rule holds good here. N is 0, 0 plus 1 is 1. So as a result, you are going to get only a singlet because it has not got any protons directly attached to it. Here, this carbon has got directly attached hydrogen, only 1. So n plus 1, 1 plus 1. So you are going to get a doublet here. Here, this carbon is directly bonded to 2 protons. 2 plus 1, 3. That's why you are going to get a triplet here. This carbon is directly attached to 3 protons. N plus 1, that is 3 plus 1. You are going to get a quartet here. So, as in the unlike proton decoupling, wherein you will see only singlets, in off-resonance decoupling, you will see multiplicity is based on the number of hydrogens directly attached to the carbon. Next, we will take some examples to see how off-resonance decoupling will be observed. This is a ketone, ethyl-methyl ketone. We will see the off-resonance decoupled spectra, how we are going to get this. This is CH3, so that means this carbon has got 3 directly bonded hydrogens. So 3 plus 1 is 4. As a result, we are going to get a quartet. This is carbonyl C double bond O. It has not got any hydrogen attached to it. So N plus 1, that is 0 plus 1, 1. We are going to get a singlet here. CH2, 2 plus 1, 3 triplet. Here CH3, 3 plus 1, 4 quartet. This is the off-resonance decoupled CMR spectra of ethyl-methyl ketone that will have various multiplicities of singlet, triplet and quartet. We will take another example here. In this case, if you see here, when you take off-resonance decoupled NMR spectra, it is shown in different colors, and this is aldehyde group COH. Only one H is attached to carbon, so 1 plus 1 is 2. That is, this aldehyde group will give a doublet. This is second carbon. Second carbon has got only one hydrogen directly attached to it. 1 plus 1 is 2, doublet. Here the same case, doublet. Here this is a quaternary carbon. This is also a quaternary carbon. We do not have any hydrogen attached to the quaternary carbon, or we will call it as C1 phenyl. So C1 phenyl or quaternary carbon does not have any directly attached hydrogen. As a result, you are going to get a singlet. This is CH2, 2 hydrogens are attached to this carbon. That's why N plus 1, 2 plus 1 is 3, triplet. Here 3 hydrogens are attached to methyl, 3 plus 1 is 4. That is, you are going to get a quartet. This is the off-resonance decoupled CMR spectra. For the same compound, if you record proton decoupling or noise decoupling, what we are going to get? We are going to get only singlets. So how many carbons are there? There are 9 carbons in this compound. So you won't be expecting 9 single peaks or 9 singlets. Rather, you are going to get 7 singlets, because carbon number 2 and 6, carbon number 3 and 5, they are symmetrical or identical. As a result of that, you are going to get only 1 singlet for these 2, 1 singlet for these 2. So 1, 2, 3, 4, 5, 6, 7. Though there are 9 carbons in this molecule, we are going to observe only 7 singlets here. This is the main difference between proton decoupling and off-resonance decoupling. That is best shown in this example. This is proton decoupled spectra, and this is off-resonance decoupled spectra. Here the carbons are labeled as A, B, C, D. Here this is A. So when you record proton decoupled, there will be no coupling between C13 and 1H. As a result, you should get only singlet. There are 4 different types of carbons. That's why you are getting 4 singlets in the noise decoupling experiment. So the first one is off resonance, whereas second one is proton decoupled spectra. 2, here also 2. This is proton decoupled. We are going to see only singlets. When you do off resonance, see here A is CH3, 3 plus 1 is 4. So A should have a quartet. See here, A has got 4 peaks, that is a quartet. Here B should also give a quartet. B is giving a quartet. C, it should give a triplet. C is giving a triplet. D, it has not got any hydrogen, that means it should give a singlet. It is giving a singlet. So this is the appearance of proton decoupled and off resonance decoupled NMR spectra of any sample that you take here. Next, we will study about the line intensities. What is the meaning of this line intensity? Line, it is here nothing but the signal or the peak. What will be the intensity of the peak? What will be the intensity of the signal? And that is called line intensity. Here you are going to get 2 types of intensities, low intensity and high intensity. If the carbon is directly bonded to hydrogen, then you will see that that peak will give a very sharp intensity. If the carbon does not has any hydrogen attached to it, then such carbons will result in low intensity peaks. So here line intensity, we can recognize the carbons that do not bear protons. In PMR, what we do is number of nuclei in any environment can be measured by integration of the areas under each peak. But in CMR, as I told you already, integration is not possible or not observed. It is because of two reasons. One reason is carbon experience different relaxation time in different environments. Say for example, if the carbon has got hydrogen, the relaxation time will be different. If the carbon does not has got hydrogen, the relaxation time will be different. Because of the varying relaxation time, the carbon will experience different relaxation times in different environments. As a result of that, you cannot integrate CMR. That means you cannot count how many number of carbons are there in the molecule. The next reason for this is here the NOE, that is nuclear overhauser effect, tends to increase the line intensities of those carbons that will bear protons and to leave other carbons unaltered. That means to say those carbons which are directly attached with the protons, they will be showing very good NOE effect. As a result of NOE effect, the line intensity will be very high. That means you will get very good narrow peaks or multiplets. Whereas if the carbons, say carbonyl carbon, quaternary carbon or C1 phenyl, they will be not showing very good intensity because those carbons do not bear any directly attached proton. As a result of that, there will be less NOE. Lesser the NOE, lesser will be the line intensities. In CMR spectrum, the presence of carbons which do not bear protons, that means carbonyl carbon, quaternary carbon or phenyl carbon, can be usually recognized from their low intensities. So in any CMR spectra, if you see very small peaks or low intensity peaks, you can easily guess that such peaks could be a result of carbonyl or quaternary carbon or phenyl C1 in the molecule. These carbons show lowered intensities because of very long relaxation times. Because these carbons that do not bear any protons, they will have or they will show very long relaxation times, and they will also observe very small NOE effect. Because of these two, the line intensities will be very small. So the smaller the intensities, you can say that those could be due to carbonyl carbon, quaternary carbon or C1 phenyl. That means any carbon which do not bear protons. Usually carbocations also, they will show low intensity peaks. On the other hand, if the carbons bear any protons, then they will have shorter relaxation time. Shorter the relaxation time, the NOE experience also will be high. Because of that, there will be very enhanced line intensities of such carbons in the molecule. Next is deuterium coupling. We have seen that in case of proton NMR, we are going to use solvents for recording NMR spectrum. The solvents, say for example chloroform, CHCl3, that H will also involve in coupling. As a result of that, we replace or we exchange that H by D by means of deuterium coupling. So CHCl3 becomes CdCl3. As a result of that, the peak from the solvent will not be seen in the proton NMR spectrum. Whereas in the case of carbon NMR, that is not possible, because even if you deuterate the solvent, say for example CdCl3, C6D6, this is benzene, this is chloroform. So H is replaced by D, here H is replaced by D. We have got carbon, and this carbon cannot be replaced by any other element or any other isotope. As a result of that, this will have very long relaxation times, and hence the peak intensity resulting from the solvents will be very less. The solvent peaks in the NMR spectra are of low intensity because of the very long relaxation time and also small NOE effect. So deuterated solvents will also give rise to C13 NMR signal, which are split by coupling with the deuterium, because deuterium has also got the spin quantum number of I, and the multiplicity of resulting from the solvent can be calculated by the general formula 2Ni plus 1. N is number of carbons and I for deuterium is 1. So 2Ni plus 1 is the general formula in order to calculate the multiplicity of the solvent. We will see how we can do that. Say for example, in any solvent, if there is only one D, as in the case of CdCl3 or C6D6, don't get confused here, there are 6 Ds. What you have to understand is one carbon is attached to 1 deuterium. So that is why we say that it is 1. So substitute 1, N is equal to 1 here because each carbon is attached to only 1 D. So here 2 into 1 into I for D is 1. So 2 into 1 into 1 is 2 plus 1. 2 plus 1 is 3. That's why CdCl3C6D6 deuterated benzene, deuterated chloroform always will give a triplet in the intensity ratio of 1:1:1. I'll show that in the next slide. Whereas if there are 3 deuterium attached to carbon, as in the case of acetone or dimethyl sulfoxide, CH3COCH3 is acetone. If you deuterate acetone, you will get CD3COCD3. CH3SOCH3 is dimethyl sulfoxide. If you deuterate that, you will get CD3SOCD3. And here each carbon has got 3 deuterium. So N is equal to 3 here. So substitute 2 into 3, 6. 6 into 1, I is 1. 2 into 3, 6. 6 into 1 is 6. 6 plus 1 is 7. So it will result in the formation of a septet. So whenever you use acetone, deuterated acetone or deuterated DMSO, dimethyl sulfoxide, abbreviated as DMSO, you will get a septet with the line intensities of 1:3:6:7:6:3:1. We will see what is that here. Here it is the solvent peak CdCl3. Here only 1 D is attached to the carbon. That's why it is 1. 2 into 1 into 1 plus 1. That is 2 plus 1 is 3. You are going to get a triplet. See here in the ratio of 1:1. That means almost all the 3 peaks are of the same intensity. If you see 3 peaks, that is triplet in the NMR in the C13 NMR spectrum, you can say that it is the result of CdCl3 peak. Say for example, if you use deuterated acetone or deuterated dimethyl sulfoxide, it is DMSO. So here 3 deuterium is attached to carbon and hence N is equal to 3. 2 into 3 into 1, 6. 6 plus 1 is 7. So 7 is septet. That will be in the ratio of 1:3:6:7:6:3:1. You are going to get a septet here. So if you see a septet in any C13 NMR spectrum, you can say that it is as a result of using a deuterated acetone or deuterated dimethyl sulfoxide or any other solvent having 3 deuterium attached to carbon. That will be the result of this septet. And if there is only one, you are going to get a triplet here. So these are the solvent peaks. Solvent will also give peaks here because solvents will have carbon and that carbon will also show the multiplicity. Because of the multiplicity, you will see the solvent peaks in the C13 NMR spectrum. That you should not get confused with the peaks that you are going to get for the sample. So before you use C13 NMR for the identification of organic compounds, you should have the knowledge of solvent peaks that arise in the C13 NMR spectrum. So this is not usually observed in case of proton NMR because we are going to remove proton by replacing it by deuterium. Deuterium is not seen because it has not got any magnetic moment and hence that will not be observed usually in the proton NMR spectra. Next is chemical shift equivalence. So chemical shift equivalence is nothing but chemical equivalence that we have seen in the proton NMR. The same thing holds good here also. That means if the carbon is present in the same atmosphere, then we will call that as chemically equivalent carbon. So instead of getting different peaks, since all the carbons are present in the same environment, you are going to get only one peak here. So this is usually seen in the proton decoupled CMR spectra, and that will give very useful information for the presence of symmetry in the organic molecules. So presence of equivalent carbon atom in a molecule results in the simplification of the spectra. We will take this. This is bromo-trimethyl methane. Here there are 2 types of carbons. One is quaternary carbon and the other is methyl carbon. Because all the 3 methyl groups are present in the same chemical environment, so all the 3 methyl will appear as only one singlet and this carbon will appear as another singlet. So you are going to get only 2 peaks. But in principle, we have got 4 carbons. That means you cannot expect 4 different types of peaks or signals. Instead of 4, we are going to get only 2 because of the presence of symmetry in the molecule. So presence of symmetry in the molecule can be resulting in simplification of the complex spectrum. This is another example, phenyl ethyl phenyl, ethyl benzyl benzoate. Here there are 10 carbon atoms, so you cannot expect 10 peaks. We have to check for the symmetry in the molecule or chemically equivalent carbons. Say this is 1, 2 and 6 are present in the same chemical atmosphere, 3 and 5 are appearing in the same chemical atmosphere. So as a result, we are going to observe 8 peaks instead of 10 peaks in the compound. We will see how this CH3 is different, CH2, COO is different, CH2 is different, this carbon is different, whereas these two is same, these two same, and this fourth carbon is different. So 4 will appear as only 2. So instead of 10 peaks, you are going to get 8 peaks in the C13 NMR spectrum. So this is all about chemical shift equivalence. That means if there is any symmetrical carbons present in the molecule, and that will give only one peak, thus resulting in the formation of a simplified C13 NMR spectrum. So lesser the complexity, more enhanced will be the structural elucidation of organic compounds. Not only the symmetrical carbons, and also by using C13 NMR spectra, you can identify whether the given isomer is ortho, meta or para just by observing the number of signals present in the C13 NMR spectrum. Say for example, we have taken xylene, this is xylene. So if two methyl groups are attached to benzene, then it is called xylene. Xylene, it occurs in 3 isomers, ortho, meta and para isomer. So this is ortho isomer, orthoxylene, metaxylene and paraxylene. So when you scan C13 NMR for orthoxylene, you are going to get 4 signals. How we are going to get 4 signals? This CH3 1, these 2 carbons 1, these 2 1 and these 2 1. 1, 2, 3, 4. So if I give you a sample of xylene and ask you to identify which isomer to that that xylene belong to, you simply scan the C13 NMR spectrum. If you get 4 signals, you can say simply that this xylene is orthoxylene. Similarly, if you get 5 signals, then you can say that it is metaxylene. How metaxylene? 5 signals, 1, 1. These 2 methyls are present in the same environment, and hence you are going to get only 1 signal, 1, 2, here, these 2 carbons 3, these 2 carbons 4, and this carbon is 5. So you are going to get 5 signals. If you get 5 signals in the proton NMR, sorry, in C13 NMR spectra of xylene, then you can clearly confirm that it is from metaxylene. Similarly, for paraxylene, you are going to get very less number of signals. That means only 3 you are going to get. How 3? This CH3, both are present in the same environment. That's why you are going to get only 1 signal. This is 2, and all the 4 protons of the aromatic ring, that comes as only 1 singlet. As a result of that, we are going to get only 3 signals. Usually, for symmetrically disubstituted isomer, that is para isomer, if it is same substitution, if there is any difference in substitution pattern, the number of signals will increase. If the symmetrically disubstituted benzene, if you take, then the lesser will be the number of peaks in the para isomer. Similarly, hydroxyacetophenone, it exists in 3 isomers, ortho, meta and para. Here, ortho and meta will give 8 signals, whereas para will give 6 signals. So how it is done? For the ortho isomer, 1, 2, 3, 4, 5, 6, 7, 8. Here, all the carbon atoms are present in different environment. That results in 8 different signals. If you see 8 signals, you can say that it is ortho or meta. Even meta, you are going to get 8 signals. How it is? 1, 2, 3, 4, 5, 6, 7, 8. All the 8 carbons are present in different atmosphere. Whereas coming to para isomer, you are going to get lesser number of signals, because 1, 2, 3, these 2 carbons are present in the same atmosphere. That's why you are going to get only 1. So 1, 2, 3, 4. Here these 2 are same, 5, and this is 6. You are going to get very small or lesser number of signals for the para isomer, as I said earlier. Another example to distinguish between cis and trans. This is trimethyl cyclohexane. We know that cyclohexane exists in chair and board form, and this is the chair form of trimethyl cyclohexane. And here this is cis trimethyl cyclohexane. Here all the methyl groups are present as equatorial. You know that hydrogen cyclohexane will present in axial and equatorial position. In the same way, this methyl are present in equatorial position. So all the three methyls are in equatorial. That's why all the three methyl will give only one signal. Then the carbon to which methyl groups are attached, that will give one signal, that is CH, and all the CH2s are present in the same atmosphere. That means you are going to get only three signals for cis isomer. Whereas for cis trans isomer, see here Y trans, because these two are equatorial, whereas this methyl is axial. That's why it is cis and trans. 1, 3 we are distinguishing. Here both 1 and 3 we have got equatorial. That's why same side cis. Here 1 and 3, 1 is cis, 1 is trans. As a result of that, this isomer is 1 cis 3 trans trimethyl cyclohexane. We will see how many peaks we are going to get in the carbon 13 NMR spectrum of this cis trans isomer. Here there are two equatorial methyls. That's why one peak. The carbon to which these equatorial methyls are attached, 2. Here this axial methyl, 3. The carbon to which axial methyl is attached, 4. And here 2 CH2s are present in one atmosphere, 5. And this CH2s are present in different atmosphere, 6. That means where if cis trans is taken, you are going to get 6 signals. If cis is taken, you are going to get 3 signals. So if you are given trimethyl cyclohexane and ask you to identify which is which based on C13 NMR, you can simply say lesser the number of carbons, that means it is a cis isomer. More number of carbon peaks, you can say that it is cis trans isomer. This is how C13 NMR is highly useful in elucidating the or in distinguishing the isomers between ortho meta para or cis and trans. That is the main application of C13 NMR spectroscopy. Having learned all this, now we have to move on to learn the chemical shift values for the C13 NMR in the same way that we have done for the proton NMR. But before we go for this, please remember that for proton NMR, the scale is very, very small. It is not well resolved. It is only between 0 to 20, or normally we say it is 0 to 12 delta. Whereas for C13 NMR, the scale is very, very large. It is 0 to 200, almost 10 times greater than that of the proton. As a result of that, you are going to get beautifully resolved spectra, unlike your proton. In proton, you will see that there will be more number of overlappings, but in carbon, you won't see such overlappings because of the well resolution of the scale. So this is the scale 0 to 200 or 220. Sometimes it goes up to 220 also. We will see what type of carbons will show 220 or higher de-shielded value, and what kind of carbons will show lesser chemical shift value or shielded values. So we can, because it is 0 to 200 scale on an approximate, the imaginary line is drawn at 100. Whatever comes towards the right, it is called as saturated carbon. Whatever comes to the left of the scale, that is called unsaturated carbon. Here there is an exception of acetylene. So here also we have got primary carbon, primary methyl, secondary methyl, tertiary methyl. So primary methyl will have lesser value than secondary. Secondary will have lesser value than primary. That means as the number of R groups increases, the chemical shift value also increases. We will see the approximate chemical shift values in a short while from now. We will see just the range here, and this is either alcohol or ether. Then that will be between 62 to 35. And if there are any halides or halogens attached to the carbon, then it will vary right from 20 up to 85 or 90. If it is an alkyne, that is acetylene kind of molecule, and such carbons will have values between 70 to 90. So except this, all the carbons are saturated carbons. That means they are sp3 hybridized. Coming to the left side of the scale, here we will have more or less unsaturated carbon, that is sp2 hybridized carbon. If it is alkenic carbon, then the value will be 110 to 150. If it is aromatic carbon, then also the value will be 120 to 150. If it is a nitrile carbon, then the value is around 130. Then if it is carbonyl, among carbonyl, you should clearly identify here based on the functional group present in carbonyl, the chemical shift value varies. So if it is amide carbonyl, the value is around 150. If it is ester carbonyl, it is also around 170. If it is carboxylic carbonyl, then the value will be around 180. And if it is aldehydic or ketonic carbonyl, then the value will be very, very high, touching up to 220 delta. Now we will see in this chart how the chemical shift value varies for different kinds of carbons based on the functional group it is attached to. So even here the solvent used here is tetramethylsilane as that of your proton NMR. So we know that in tetramethylsilane, all the methyl groups, tetramethyl, there are 4 methyl groups, all the methyl groups are present in the identical atmosphere. As a result of that, it will give 0 delta. Even in proton NMR, it will give 0. Even in carbon, it is giving 0. Primary methyl, it will be 8 to 30. It depends on the functional group or the nature of the molecule. You cannot always stick to one particular value for particular kind of carbon or proton. Depending on the nature of the sample, nature of the organic compound, the value will shift, but definitely it will be within this range. If it is secondary alkyl carbon, then it will be 15 to 55. If it is tertiary alkyl carbon, then it will be 20 to 60. Here we can see that as the number of R's increases, the chemical shift value also increases. Then if it is quaternary carbon, you will see that it is between 30 to 50. Always remember quaternary carbons, how to identify them? Because of the low intensity. If you get a low intense peak, then you can say that it may be around 30 to 50. You can say that it may be due to quaternary carbon. Then if there are any halogens or halides, if it is iodo 20 to 40, if it is bromo 25 to 65, if it is chloro 35 to 80. Then if there is any ether function, then it will be between 40 to 80. If it is any nitrile function, Cn, so here the value is given only for the C, and that's why all the C's are marked in red. So it is not proton NMR, it is clearly carbon 13 NMR. That's why all the carbons are highlighted in red. So it is for nitrile carbon, it is 30 to 65. It is alkenic carbon 100 to 150. That means the conjugation increases the chemical shift value. Here there will be more conjugation because of the ring current. The chemical shift value will also be very, very high. So if it is aromatic carbon, then it will be 110 to 170. The range is very, very large because we have got electron donating groups and electron releasing groups. If there is any electron releasing group, then you will have smaller delta values for this. If there is any electron withdrawing group, then you will have larger delta for this. That we will see when we take up problems. And this is imine, C double bond N, 150 to 170. This is nitrile, 110 to 140. This is amide carbonyl, 155 to 185. And the carboxylic acid carbonyl, ester carbonyl carbon, carboxylic acid carbon, the range will be between 165 to 185. And if it is aldehydic or ketonic carbonyl carbon, then the value will be very, very high in the C13 NMR spectrum. That will be towards completely the left side of the spectrum. So whatever the peaks you get on the left side of the spectrum, completely dead end of the spectrum, you can say that that may be due to carbonyl carbon, and the range will be 190 to 220. So you need to memorize these values. You don't have to memorize the exact value, but you need to know the range for assigning the carbon value when the structural elucidation or composite problem is given for solving purpose. So these are the chemical shift value, and as I said, this is approximate chemical shift values for the C13 NMR, and that you have to remember. Thank you very much. We will see in the next module for solving some of the problems related to C13 NMR. Thank you very much.